Okay, I'm going to give a quick introduction to the Weighing Jupiter lab, but before I get into the specifics of that, let's go through some of the basic functions in Stellarium. So this is the program Stellarium. I brought it up here. There's lots of controls. It's very customizable. The first thing that you'll want to customize is the location where you're from. And you'll see here it says Earth, Concord, New Hampshire. That's one of the settings that I've already adjusted. And so every time I open up the program, it comes up with Earth, Concord, New Hampshire. But you can specify where you want it to be. Now, over on the left-hand side of the screen, if you hover over here, click over here, it will bring up a menu. And the top one is location window. So that's the one I'm going to go to in a second. But then there's date, time, sky and viewing options, search window, configuration, and then help over here on the left. But let's go to the location first. You can set your location to be anywhere you want. You can even put in the latitude and longitude specifically. So if you're in a place that doesn't show up in the database over here, then you can put in your latitude. So Google search latitude and longitude. Google search your location, and you should be able to find these coordinates, and you can put them in exactly so the Stellarium software knows exactly where you are. So that's already done here. I'm near Concord, New Hampshire, so Concord, New Hampshire is one of the presets. If you're in that vicinity, you should be able to find Concord in the list over here. Okay, so once you've set your location, Stellarium knows where you are, and you can click and drag around the screen, and it will show you what the sky looks like at a specific time. Now you notice the time is here, so this is the current time. It's May 20th, 2020, and the time of day is 11:28 and 3 seconds, 4 seconds. So it keeps going along with the current time. Unless I pause it, so let me go down here and pause it, and then it will pause the time. Okay, so what if you want to go to a specific time? Let me go back over to the right-hand side here. The date time window, and I'm going to leave this one up, and you can move it around so it's out of your way. You can set the date time to be anything you want. If I want to know what the sky looks like next year on this day, I just go to 2021, 2022, 2023. Okay, it's not changing very much, but you can adjust the year, the day, the month, the day, and then the hour and minutes and seconds, all right here. Okay, so right now we're not seeing a lot in the sky because it's daytime, and the thing that dominates the sky during daytime is the sun. It's so bright that nothing else in the sky is visible. So maybe I want to fast forward until the night. So I can click hour by hour, and it'll show me how my sky is changing. Eventually, sun's going to go down, and the sky is going to get dark, and the stars will appear. But if I want to, let's go back to the present. If I want to, I can make the sky dark anytime, and that's another setting down here at the bottom. And now let's look at the bottom row. I can put constellation lines on. I can put the names, the labels for the constellations. If I want them to show up as pictures, right? So right now there's lines, and good luck figuring out what the actual picture is. If you want to see what the picture is, you can show the pictures as well. You can put grid lines, one that's oriented with the equator, the equatorial grid. You can take that away, put on an azimuthal grid, which is based on sort of your own personal setting, like it's relative to where you are on the Earth. Or maybe you don't want any of those grids on there. And for the lab that we're going to do, you won't need the grids on there. But back to what I was saying about you can make it dark at any time. Let me take away the pictures here. You can make it dark at any time by getting rid of the ground and the atmosphere. Okay. And so now we're just seeing into space, what it would be like if we could see through the atmosphere and see through the ground. Okay. Now, there's other things here. We'll come back to a couple of the other ones. One thing I should mention before, if you take this out to do some observing, a really nice feature is you can go into night mode. So if you have this app on your phone, which I do, and I take it out to do observing all the time, I can put in night mode, which makes the colors show up as red light, which is easier on your eyes to adjust back and forth from the sky to the screen compared to like the brighter white that the stars appear in its sort of original setting. All right, so let's come back to this side. Location window we've looked at, date and time window, I've kept that up. Sky and viewing options window. I think in one of the slides from the first week, I mentioned that the constellations are different for different cultures. Well, in here you can actually change the culture that you're centered on. So it's set up to do Western constellations by default, but if I want to look at what is the sky in the Arabic perspective, you can change it to whichever one, Chinese, Maori, Navajo. You can change the constellation. Now you'll find that not every grouping of stars has a picture in every culture. But if you're interested in this, you can take a look at the sky from different perspectives. You can also change what your landscape looks like. You can make it look like you're on Mars, or let's put the ground back on. Otherwise, it won't look anything. You can make it look like you're on Saturn, what Saturn's atmosphere would look like. You can have trees around you. You can be on the ocean. You can be on the moon. So you can change some of those things. Like I said, it's very customizable. Let's go to the ocean. It's the least obstructed view. Okay, so I'm going to close that down. Search window. Now let's get into the lab that we're actually going to do. You're going to center in on Jupiter and watch the Galilean moons, the four largest moons of Jupiter, orbit around it. So I need to find Jupiter. And I can do that from the search window by typing in Jupiter. And then when you hit enter, it will center on Jupiter. Okay, so right now at this current location, at this time of day, Jupiter would be below the horizon down here. So for the lab, you don't care whether it's day or night. You just want to watch the moons orbit around. So I am going to get rid of the atmosphere and the ground again. And now I can see Jupiter's here. Saturn's not far from it in the sky right now. Let's zoom in. Okay, so I'm using my scroll on the mouse to zoom in. And when you zoom in close enough, you'll see the moons of Jupiter appear. So we have Europa, Ganymede, Callisto, and Io. Those are the four Galilean moons. Now, you're going to be making measurements of essentially two properties of these moons: how far away they are from Jupiter and how much time it takes them to make a complete orbit around. So let's watch the orbits, and I'll do that by just clicking up on the time so you can watch them move over time. Okay, so as I'm clicking, the positions of these moons are changing. This is something Galileo was able to observe in his telescope. And then he concluded that the moons are in orbit around Jupiter. Okay, so now any given time, the order of them might change. But if you watch a full orbit, you'll see that Io is the closest, Europa is the next, Ganymede is the next, and Callisto is the furthest of the four Galilean moons. So I'm going to pick one to show you as an example, and then you'll do this same thing for all four of the Galilean moons. So let's transition over here. This is the spreadsheet, the Weighing Jupiter spreadsheet. there's a section here for each of the 4 moons. Let's just pick one. I'll pick Europa, and let's go through the data you need to enter in. So for Europa, we need to first set the scale. And you can set the scale by measuring the size of Jupiter on your screen. And that's going to change depending on how far you're zoomed in. So if I zoom in further, Jupiter gets bigger. If I zoom farther away, Jupiter gets smaller. So I want to zoom in to a location where I'll be able to see the full orbit of Europa. So let me click forward until Europa goes almost off the screen. So there it might be off the screen. So I need to zoom in a little bit further. I want to be able to capture the full orbit of Jupiter. And it looks like at this level of zoom, I'll be able to do it. It's never going to leave the screen at this level. All right, so what I need to do first is measure the size of Jupiter. So you can't see this, but I have a ruler in my hand. I'm putting the ruler up to the screen, and I'm measuring the diameter across Jupiter, and it's just under 3 centimeters. Looks like about 2.7 centimeters. So I'm going to go into the spreadsheet on Europa and put in 2.7 centimeters. The actual size of Jupiter, diameter of Jupiter, is 140,000 kilometers. So what I've done is I've given the information of how big is it on my screen, and so now I have a scale factor, what we call a scale factor, a way to convert between centimeters measured on the screen and kilometers in real life. So every centimeter on the screen corresponds to this many kilometers in real life. Okay, next I need to find a starting point and an end point for an orbit. Now orbits are basically circles, so the starting and end point are arbitrary. You could pick any point to be the starting and end point. The key is that the starting point and end point are one complete loop apart. So there's a couple of ways to do this. You could start when the moon is right in front of Jupiter, right behind Jupiter, and then wait for it to go back to that point. But I want to also measure the semi-major axis, its furthest extent from Jupiter. So I'm going to pick my starting point to be a point where it's the farthest away from Jupiter. So let me scroll around here, and at the same time, again, you can't see this, but I'm holding the ruler up to the screen so I can see how far roughly Europa is away from Jupiter. And I want to stop at a point where it's the farthest it's going to be. Oops. If you do what I just did, which is lose the planet, you just search for it again, and it will recenter on it. I just clicked off of the screen, and so it drifted off of Jupiter. But you can always put it back on, and it stays as long as I didn't change my zoom level. It stays the same. Okay, so anyway, right about here is where it's at. I think maybe a step further. Okay, right here is it's at its furthest extent from Jupiter, and I'm measuring from the center of Jupiter to Europa, and it looks to me to be 12.8 centimeters. Okay, so that's my starting point, 12.8 centimeters. And if I look at the day, hour, minute, it is the 25th day, the 16th hour, this is military time, and the 28th minute. Okay, so that's my starting point for Jupiter. The end point. Now for the end point, I need to fast forward until it comes back to here. roughly the same distance away. Its furthest extent over on the right-hand side. So I'll do some clicking. It's going behind Jupiter. Eventually it should come back in front of Jupiter. Okay, so it passed in front of Jupiter, and now I'm waiting for it to get as far on the right-hand side as it can. And when it starts to get smaller again, that's when. Okay, so it looks like about there, and I'm back again. Let's see, one. Yeah, so I'm back again at 12.8 centimeters again. Okay, and what day is it? Now we're at the 29th day. The hour is 3, and the minutes are again 28. Okay, so it's calculated for me here the period of Europa's orbit. It takes 298,800 seconds to make one orbit, to go from this starting point to this end point. 298,800 seconds. One caveat here is that I'm starting kind of near the end of the month with these observations, and you'll notice I got pretty close to the end of the month, right? I got close to May 31st. I would recommend, just to make sure that you stay within the same month, that you start your observations somewhere like at the beginning of June. And that's because if the math is set up so on the spreadsheet so that it's assuming you're staying in the same month. So if you change from one month to the next, you go from like day 20, let's say it went from day 25 to day 4. Well, it will spit out a really wrong answer for the number of seconds because it's not accounting for the fact that you switched into a new month. So when you do the lab, I would recommend starting on like June 1st and then fast forwarding from there. And that will guarantee that the moon orbits are all within that same month. Okay, but I kind of lucked out here. Even though I started on the 25th, I ended on the 29th. And so I'm still in the month of May. If I had done the same thing for Ganymede, I think I would have gone into June, and definitely for Callisto. All right, so I've collected the data. You're basically doing that 4 different times. Each time, zoom into the appropriate level to capture the entire orbit, and then find a starting point, record the distance and time. So the only tool you need is a ruler, and then fast forward until you get to the end point and do the same thing. The spreadsheet will calculate the period in seconds, and let me slide this over. It should then also calculate the mass of Jupiter. So there's 2 tables, table 1 and table 2. Table 2 will calculate the mass of Jupiter using the equation in the lab instructions. So this is my value for the semi-major axis of Europa. This is its period, and then this is its mass. And hopefully you get an answer that looks pretty close to this. You can get very decent results, and that is actually very close to the true mass of Jupiter, and hopefully for all of your values, you'll get something similar. And take the average, and that's your final answer. The post-lab questions ask you to give this information. So table 1, you're going to include your results here in table 1 and in table 2, and then do some analysis. Think about the periods here compared to the moon. Think about the semi-major axis and put that into perspective, and then report on your final answer for the mass of Jupiter after you take the average of all 4. Okay, so that's the lab in a nutshell. I just thought of one more thing I should show you back here. So let's go out of this. We'll zoom back out, because you'll have some assignments where you are asked to observe, but don't just do the observations when you're assigned them. Hopefully you'll go out and observe the night sky on your own, just to kind of think about the things that we're doing in class, talking about in class. And Stellarium is a great tool for that. It should help you locate anything you might want to find. So let's put back on the ground and atmosphere. The cardinal points are like the north, south, and everything, and help you to orient yourself. Now, the first thing to do to orient yourself if you want to make any observations is identify north, south, east, and west. And you can do that by thinking about what's happening with the sun. The sun is always going to rise in the east and set in the west. Let's go back to play and date time window. So let's go back to the current time. I think I can just do that. Yeah, 20. And it's 11, around 11:30. Okay. So this is what the sky would look like if you're out on a boat right now near Concord. I don't know how you'd be on the ocean near Concord, but let's suppose we were. You're looking at the south. It's near noon, so the sun has risen in the east. It's going to eventually set over here in the west. Now to move the screen, I'm just clicking and then you can drag it anywhere you'd like. The moon should be high in the south. Okay. The sun is above that. So notice we're not quite at noon and the sun is not quite at its highest point. So if I go forward a little bit, now we're around the highest point. So noon technically refers to the time of day when the sun is at its highest, and it's usually around 12 p.m. If I keep fast forwarding, the sun is moving through the sky, and the path that it's taking in the sky, that's what we're referring to as the ecliptic. Okay. Notice also that the constellations are moving with it, right? So the sun is essentially in Taurus right now. That's what it means. You could never see Taurus because the sun is there and out and in front of it and is going to outshine the light of all of the stars that are part of Taurus. But all of those constellations move with it, and they're moving with it into the west where the sun will eventually set. And it will set, so this is 1930, so that would be 7:30 p.m. And it's light out until about 8:30 or so when the sun is below the horizon. When the sun goes below the horizon, if you look out in the sky, you should be able to see Venus and probably Mercury. They're always going to be just before the sun goes down, or just before the sun, or sorry, just after the sun goes down, or just before the sun rises is the best time to see those planets, because they're the inner planets. They're the closest to the sun, and they're always going to be near it in the sky. So if let's go to, so this is 9:30. 9:30 p.m., if you have an unobstructed view of the horizon, you should get a nice look at Venus and Mercury just below the horizon. If there are any other planets visible, they would be visible along that ecliptic line, so going through the zodiac constellations, Gemini, Cancer, from the west and into the east. Okay, let's get a slightly zoomed out view. And let's see, it doesn't look like there's any others visible right now. Might be out of luck a little bit on that. But Venus and Mercury should be able to find if you want to go looking for them. The other thing that I would say to look for and encourage you to look for is just recognizing as many constellations as you can. The zodiac is kind of the classic thing to start with. So go out at night, 9:30. You should be able to, Gemini is fairly easy to identify. Cancer and Leo. Leo's a really neat one. I mean, on the screen here it looks really small, but in real life, if you can find this pattern here, and just imagine it as a big lion laying on the ground. It's quite a dominant feature in the sky. It's really big. The same thing would be true for the Big Dipper. Okay, so the Big Dipper is up here. Okay, so if you're looking to the west, the Big Dipper is sort of facing the western horizon at this time of night, and it's part of Ursa Major, this Great Bear, which is an enormous feature in the sky. All right, if you have more questions about finding things, I'm happy to pull up Stellarium on my computer and show you what to look for and how to look for it, or just any other tips and tricks you need to use this program. I really encourage you to do as much with Stellarium as you can. It'll make the subject come to life a lot more, finding it in here and then going outside at night and trying to find it out there.